Hello. I am Brian W. Mulligan, also known as AstroBit.
And I am Sam Factor, also known as MCMC Hammer.
And we are here.
We're both grad students at UT, and we're here to present some news that's been...
All right, so first off, Congress has finally passed the 2018-2019 budget as of March 23rd, giving the largest increase in spending to astronomy since 2009. The final budget represents a substantial break from the president's proposed budget, which offered cuts to many of the programs used to fund astronomical research. As a whole, the budget includes an increase of over $2 billion to programs used for astrophysics funding, mostly for new hardware. Within NASA's budget, the James Webb Space Telescope has continued funding, though the impact of the recently announced delay in the launch has yet to be determined. The Next Generation Infrared Survey Telescope, WFIRST, has received an appropriation of $150 million despite initial indications that it would be cut. There's also a large boost within the Planetary Sciences program, in part for a mission to Europa, an icy moon of Jupiter that's a hopeful site for life. Within the NSF, overall research funding has increased, and the two major facilities funded by the NSF, LSST and the Daniel K. Inouye Solar Telescope, have received continued funding. Overall, the community is pleased to see slightly increased funding, though it doesn't fully restore the funding from before the 2009 sequester. If you would like to donate, there are tip jars located at the merchandise table. We appreciate it.
More money is always good. Yeah, so if you remember, about 2 years ago, there was a new exoplanet discovered around Proxima B, the nearest star to the Earth. And just recently, actually, the flare itself was also about 2 years ago, but just recently a study was published that detailed a research done on a flare that happened around Proxima B, which actually increased its brightness by almost 40 times brighter than its normal levels, which actually made the star Proxima B, which is normally, if you know magnitude, it's about 11th magnitude. You can't see it with your naked eye. It made it as bright, almost visible by the naked eye, of about 6.7. And this actually has some effects on the habitability or possible habitability of Proxima B. It is actually located in the habitable zone where liquid water could exist, but these very energetic flares that seem to be happening around 5 times a year, if you do the statistics, could completely erode away all of the ozone, which would protect any life on the surface from UV rays. Yeah, so even though it's in the habitable zone, it may not actually be habitable. So, sad face.
So much for our alternative plan.
But we really are still working on how these planetary atmospheres work. So there's still a little bit of chance, but it's very difficult.
All right, a special type of exploding star known as a fast-evolving luminous transient, or FELT, has been caught in the act. These types of events have been seen before, but this is the most comprehensive view that we've seen. FELTs are characterized by a rapid increase in the brightness, becoming about 1 billion times, that's with a B, as luminous as our sun over the course of a few days, and then fading away over a few weeks. A relative analogy is Anthony Scaramucci. These last about twice as long as he did. These differ from ordinary supernova in the short time that it takes to become so bright, as well as the short time in which they remain. The rapid increase in brightness suggests these events are the result of the explosion of a star crashing into material that the star has previously puffed off sometime earlier in its lifetime. Once the explosion catches up, it causes a shock wave to pass through the material that quickly heats it up. As the FELT occurs as the shock wave reaches the outer edge of the material, quickly heating it up such that we're able to see it, and then quickly cooling as the material radiates to light and expands. The observation of these were the first to see the whole process from beginning to end and confirm these are not failed supernova. These events will lead to a better understanding of the life of massive stars.
So continuing on the lines of the previous story I just talked about, if you've been paying attention to planetary atmospheres, which I don't know why you would, but we've had a couple of talks over the past few years. A lot of research has been, or a lot of telescope time has been put into looking at exoplanets' atmospheres, trying to figure out what they're made of, and a lot of telescope time has, I don't know if you want to say wasted, but they've found flat spectrum. We can't tell what's in it. There's lots of clouds and hazes. So a recent, actually, laboratory study done on Earth has been working on trying to figure out which sorts of planets might have hazes and what effect they would have on any life on the surface. So they actually built a experimental chamber that you can kind of see on the right top there, where they mix a bunch of gases together, carbon dioxide, water, methane, nitrogen, kind of run-of-the-mill gases that you might find in an atmosphere. They give it a certain temperature, so they tried a bunch of different temperatures there, shoot it through kind of a plasma thing, which ionizes the gas and gets chemical reactions going, and then they find out whether it makes hazes. And they found, actually, that most planets, unfortunately, do make hazes, but kind of counterintuitively, previously we thought that methane would be the primary driver of these hazes. Lots of carbon means hazy atmospheres. But they actually found that the water-dominant atmospheres created the most haze. So that's kind of interesting. And they found that different colors of the hazes that were produced might have an effect on the heating of the atmosphere underneath those hazes, and could have an effect on the habitability of the planets.
All right. A small galaxy that may completely lack any dark matter has been found. Using a small telescope array called Dragonfly, you can see it as essentially a bunch of cameras stuck together over here. The team imaged a distant galaxy known as NGC 2015-DF2. Always exciting names we've got. They observed the motion of globular clusters, which are compact sets of stars. Imagine 1 million stars packed between us and the next nearest star to us. So if we lived in the middle of a globular cluster, you would look out and see millions of stars instead of thousands of stars. They used these globular clusters to weigh the galaxy and found that the total amount of material required is accounted for by the stars that are visible within the galaxy. This is in contrast to all other galaxies that require about half or more of the material to be in visible dark matter. The result is controversial, with some other astronomers suggesting that they did not fully account for the limited number of globular clusters that they used, and others are suggesting that alternative theories of gravity may explain the case. If this discovery holds up, it will require an explanation of either what happened to the dark matter after the galaxy formed, or how this galaxy managed to form in the first place without any dark matter.
And finally, we have a section called Astronomy Not in the News. This is where we talk about a paper or study that has been making some noise in the astronomical community, but may not have made it all the way to the media. And this is a study, statistical study on Kepler planets. So this is a telescope that looks for the dimming of stars as a planet crosses in front of it. And recently there have been a lot of very large releases of confirmed planets due to basically a statistical analysis rather than detailed follow-up observations. Basically, they wanted to confirm thousands of planets, and it's just really not feasible to go and observe all of those with telescopes to confirm them. So they do it statistically. So we get 99% confidence that these are real. So this study went back and looked at a very specific subset of those statistically confirmed planets. So they're long period, so between 200 and 500 day orbits, and they're small planets, so about the size of Earth. And this study found that there are a lot of false positives in this kind of regime of parameter space that could potentially be misconstrued as planets. And so if you're going to statistically confirm them, you need to be very certain that you're ruling out enough of these that none of them creep through. But it's very hard to do that without also rejecting real planets. So here are two light curves. So on the x-axis is the time, and on the y-axis is brightness. And you can see there's a little bit of a dip where that blue shading is, where a planet might be. And on the top and the bottom, one of those is real, and one of those is fake. Can anyone tell the difference? I didn't think so. The top one is a real, the bottom one is fake, and this just goes to show how difficult this is. And basically the takeaway from the story is that very small planets in these long period orbits are very hard to statistically confirm, and we really need to do our due diligence and go follow them up with spectroscopy or high-resolution imaging to make sure that they're not false positives.
Or in other words, we're just making it all up.
But 90% of them are still real, just not 99%.
All right, thank you very much. That's Astronomy News for, what month are we in? April 2018. Enjoy the rest of the show. Thank you for coming.